Hello, Matt. So yet we have a homework due on Wednesday. We'll have one more homework due before the midterm, for the next midterm. 7 Wednesday. And between this Wednesday on Monday, which is October 5th, we will have no class. And midterm 2 is on October 9th, Friday, in class. So two things to point out, it's different from usual. One is that it's no class on Monday, and it seems like I will be having the midterm in class. So the barriers for those who are online. So it seems like there is no reason to not have it in class. If there are any concerns about that, contact me on email. But we can have it in class. Okay, so we talked about dipole moment, and I said that there are higher moments that will be there. So this time, let's talk about the next one, quadruple moment. I think that's a spelling. A moment of charges. And again, remember what we are about monopole moment. It could be electric charge density. It could be electric charge or magnetic charge for that matter, or even masses. Like for masses, it is not very useful because there are no negative masses. And we pointed out that if the monopole is not zero, then the dipole moment is dependent on the origin. So it is not unique, and in that sense, it's not very useful. But the definitions remain. Definitions are useful. So this is Q is Q1 plus Q2 plus Q3, so on, sum of charges. Dipole moment is a vector P, which is Q1 times the position of charge 1 plus Q2 times position of charge 2, and so on. Like to add them up. If you are having a continuous distribution, instead of this, you would do a volume integral d cube r of charge density. Let's put it primes here so that since we are, doesn't matter whether it is prime or r, since we have been using primes to represent sources, that's the way one can write that. And this will be Q again, right? Q. Dipole moment, similarly we said, is cube or prime, pretty much the same. So prime, but we multiply by r prime everywhere, so there's a weight. There's an x, so there are 3 integrals here already, and there are 3 of them. In the I direction, there is an x prime. In the y direction, there is a y prime, and so on. Next one is a quadruple moment. And as you can see, this is a scalar quantity. This is a vector quantity. It seems like the next one is maybe a quadruple moment. So this will be a Q, and this will be a dyadic in a sense. It's a tensor, so it has two vector components, or 9 vector components in a sense. So this has 3, so this will be 9. And we would like to know what this is. So that what is this? So Q1 times what, right? So this was R1. It seems like there will be 2 of them, so there's 2 R1, R1. That is correct, but we will do this in a more concrete way, and we will find it nice to define this as R1 is a vector, this R1, minus R1 square times a dyadic 1. And keep doing for so it is having 2 R's, as you see, but that is more than that. We tend to subtract that diagonal pieces out, and we will see why that definition. And the same thing here, this extends to Q, and this might be a small confusion. This is a charge, total charge. Again, I use the Q, but that represents quadruple moment, but that's a dyadic. And this will be equal to d cube of prime 3 r prime minus 1 r prime square. That will be the quadruple. Next one will be an octuple and so on, but it comes out to be very hard to write it in terms of vectors. The best you can do is go to dyadic. That is still a vector nature, but then you have to actually use index notations. Whatever we did in the first couple of these, then you have to switch over to index. That's the only way to proceed. But let's see how this comes about. Let's go back to our Fourier transformation. So not Fourier, what is it? Taylor expansion, right? Taylor expansion R plus R prime, we said was f of R plus R prime after the gradient of f of R plus 1 over 2 factorial R prime. We're going to write this 2 times. This is basically squared. Oh, let me write it as squared. and so on. And that's what we did the last two classes. And then we said, oh, there's a special function here, which is the electric potential. And let's talk about electric potential due to a point charge, which is 1 over r minus r prime. Expand this out, and I should point out, I think I might have mentioned this before, I've tried to emphasize on the fact that gravity and this comes out very similar. All these were developed in way back right after Newton gave his theories, because the people wanted to study planetary motion or astronomical studies. The moment you have three masses, you want to expand it about gravity also has 1 over r potential, and you want to solve it. And they discovered all these things right in 1700 to 1750. So it was not in electrostatics this was discovered. This was in all discovered in the context of Newtonian gravity, especially in planetary motion. That was a big challenging problems in those days. So keep working on this, do this expansion for the electric potential to the point charge, and this is q over 4 pi epsilon naught. F of r here is 1 over r minus r prime. When I set r prime equal to 0, that's just magnitude of r, which is 1 over r. That's the electric potential due to a point charge. When you place it at the origin, there's a significant simplicity when it is placed at the origin, and that's the idea in here. The next one is minus, right? Because there is this minus sign here, and r prime dotted with gradient of 1 over r again. Right? F of r is still 1 over r. So in terms of electric potential about the origin, we can do various things. And the next one, we already processed this quantity and realized that that's a dipole moment. Let's, oh, there's a q also. Q r prime, and there's a 4 pi epsilon to okay, so there's q over 4 pi epsilon naught, and that is r prime dotted with gradient of 1 over r. Right? That's what it is, I suppose, and r prime. And the next one, because there are two negative signs, that becomes a positive. There's still q over 4 pi epsilon naught. That is 1 over 2 factorial. And let me write this twice now. R prime dotted with gradient, and that is gradient dotted, let me 1 over r. I will dot the r prime here with this. There are two of them, but r prime can go through this derivative, right? So I can even write that dot on the right hand side. So that's just convenience. If this derivative does not get prime because it only gets r. That's just a convenience there, and that's a maximum one can do. So there is no ambiguity here by moving it on the other side, because this hits only on r. Right. And so on. We already processed this. Gradient of 1 over r, in fact, with the negative sign, is exact. So this is the negative gradient of an electric potential due to a point charge. So this we said was the electric field. That's r over r cubed. We already did that. Take the derivative of this, 1 over r squared, and then that's r hat. So write it as r over r cubed. And we did that. And so that was the first two expressions. So that's so if I were to write this 1 over 4 pi epsilon naught, that seems to be a factor all the way which can be pulled out. It's because we are working in the SI units. That's when it shows up. So it's Q over R. That's our electric potential to a point charge. So it's a point charge showing up. Next one is write it as Q R prime dotted with R over RQ. So this gives us a clear picture of what should be defined as the dipole moment, right? That was our guide there, that should be defined as the dipole moment. And that also is going to guide us as to what should be the quadruple moment. So plus, put this as 1 over 4 pi epsilon naught, 1 over 2 factorial, and I had to process this. So that is Q times R prime, right? But the other R prime, so there are two pieces there, right? One R prime is here, and the other R prime is on the other side. So let me write this as gradient 1 over R, which will process now, dotted with R prime. And we would like to write this as some Q here like this, times over R square or something. So that's our goal here. So let's process this quantity. Let me move the camera. Any questions at this stage? If the motivation is clear, we are trying to write this structure in such a form that we can identify something like quadruple moment clearly in there. Okay, so we move the camera to the other side. Yeah, we would like to evaluate gradient of 1 over R. It's a dyadic structure in there. It's not like a vector. That's gradient of minus 1 over R square times gradient of R, right? That's how you do that. And we know that gradient of R is equal to R hat, which can be written as vector R over R. Using that in here, this gives us negative gradient, and this is vector R over RQ. No dot product there again. So dyadic. There are two structures here. Either I can hit the numerator or the denominator. So this is first I hit the numerator. So it's that's 1 over R cube if you want, and this I can move this way or that way. It doesn't matter where I keep this R cube. This is a scalar quantity. And the next one has to hit this R cube. So this is minus gradient of 1 over cube. In this case, it is important that I keep this on the left because the vector nature on the left and the vector nature on the right is important. It will turn out that it is symmetric in this case, but in general, you have to keep this onto the left because this is the left indexed vector. But this can be done using the same idea, but before that, gradient operator acting on the position coordinate, that's a completeness statement, and that's a unit diagram that we have used before. And here, this is gradient of 1 over R cube is minus 3 over R raised to 4. times gradient of the magnitude of r. But that's r hat. So it's minus 3 r hat over r raised to 4, which is the same as minus 3 vector r over r raised to 5. So that gives me minus, this is 1 over r cubed, and this is plus now 3 times vector r over r raised to 5, then another vector r raised to 5. You see that structure 3r minus 1 showing up, defined in the quadruple moment. So this is 1 over r raised to 5, 3 times vector r minus dyadic times r square, multiplied by an r square, divided by an r square there, divided by r raised to 5. That's the 20. And we see that structure showing up in the dipole moment of if you're doing electric field due to a dipole moment, which was part of your homework. The same structure showed up, but of course it was dotted and there was some dot product. Let's do a small trick in this. So what we are encountering in the expansion out there is, before that, any questions? Yeah. So what we are encountering in the expansion out there is this dotted with r prime. We are take r prime dotted with 1 over r times r prime. And notice there is a symmetry in this, so this dyadic is very symmetric. Whether I move this r this way, that way, it doesn't matter. Typically, dyadics are not symmetric, but this is a symmetric dyadic. So if I were to dot this dyadic on left-hand side on both sides, so r prime will dot with the left vector, r prime on the right-hand side will dot with the right vector. And here this will dot, so this is r prime dotted with 1 dotted with r prime. What is that equal to? Square, because 1 multiplied by vector gives you the vector itself. So this is r prime dotted with r prime, which is r prime square. So if we notice, if we use those properties, it seems like this is 3 r dotted with r prime dotted with r and r dotted with r prime minus of this is r prime square and divided by r raised to 5. That's what it looks like. Let me write this in 2 steps actually, just to emphasize what I'm doing here. So this is r prime divided with 3 square dotted with r prime over r raised to 5, which is equal to 3 r prime dotted with r dotted with r prime minus r prime square and r square. That's really correct. I just wrote it in 2 steps. But now I do a small symmetry trick here. Now I undo this again. So this was coming as a dyadic, and I pulled that r primes in. But this time I pull out the r's out. This is r dotted with 3 times r prime minus r prime square times 1 dotted with r. Slight difference between these two notice. In this case, r's are pulled out. In this case, r primes are pulled out. And this we will interpret as, so let me multiply by a q from outside, q from outside, and let's say q from outside. And I define this to be, so this is vector r dotted with a dyadic now, which is going to be called the quadruple moment, dotted with r observation points times r raised to 5 where, so in this way of looking at it, now we define, right? This is the definition. Define q to be equal to, notice the difference, this is sort of repeating itself, but this is charge q, this is quadruple moment q. So it's one is scalar, one is dyadic, so there shouldn't be any confusion that it's the same. So q times 3 r prime minus r prime square times 1. That's the quadruple moment of a point charge. So if it is right at the origin, if the point charge is at the origin, then this is 0, that's 0, there's no quadruple moment. But the moment you're away from the origin, that is a quadruple moment. Pretty much like moment of inertia. That is a concept of moment of inertia. The moment you have a mass element away from that configuration. So that's how you motivate that term coming in there. So if I go back to my first code, okay, if I go back to the first piece in there, that means that this whole thing can be expressed as a quadruple moment. So this is 1 over 4 pi epsilon naught. This is q over r plus 1 over 4 pi epsilon naught times p dotted with r, is bringing in the dipole moment due to a point charge. If it is away from the origin, even a point charge, even a single point charge can have a dipole moment. And now we have a quadruple moment, which is 1 over 2 factorial. And you write this as r dotted with q. over r raised to 5. See the pi term r cube r raised to 5 scalar vector dyadic or tensor of rank 0, tensor of rank 1, tensor of rank 2, and so on are showing up. And this keeps going, where Q here is for a point charge this, and now we have to see how does it generalize to more than one charges. If I want to have more than one charges, it is pretty straightforward. Notice what I do. If I have more than one charge, I will say the electric potential now is I is equal to 1 to n. I put an I underneath all these Q's, and instead of prime, I say r prime I. Right? For each charge, it has a position Ri. So, and I just have to repeat that whole thing here. So this is sum. Let me write only the last one instead of repeating everything. So this is sum Q I over 4 pi epsilon naught 1 over observation point times the source point, but now source point there are n source points, and this is 1 over 4 pi epsilon naught. This is now the total charge Q over R, because total charge is Q1 plus Q2 plus Q3. The sum of the charges becomes charge Q. Here, this is the dipole moment itself, but this time the dipole moment is interpreted as the sum of Q1, R1, Q2, R2, and so on. Q plus the same thing here. Now 1 over 4 pi epsilon naught, 1 over 2 factorial, pretty much same, right? I mean, interpretation here has changed. The expressions look exactly the same. And instead of summation, if I had done an integral of with respect to rho, then I get the right hand side relation, where I get a continuous charge distribution. That's all good. Now let's try to do some simple examples where we explicitly try to see what is the quadruple moment for a certain charge distribution. So let's, and that is what your homework is about. You do specific. So typically, what I do in exam is I give you some 3 charges, 3 or 5 charges. I can give you as many charges as you want, and you should be able to calculate what is the total charge, which is the easiest. You just add them. You should be able to calculate the dipole moment for it, find the positions and add them. And this comes out to be harder, but most of the times I think it goes through easily, and you have to do it as matrices. That's only. So let's see how that goes through. So let's take the simple scenario that we were doing last time. So let's say there are charges in a line. So this is 1, and that is 2, and that is 3. Let's say this is minus 2q. This is plus q, and this is plus q. And
can you move the camera?
Oh, can you move? Oh yeah, it did not come back in, right? Yes.
All right, thank you.
That will help, huh? Sorry for that. Yeah. You interrupt me these times. Yeah. Okay. So I was telling. We would like to, so there's an example where you calculate this for specific case, right? And we did a very similar example last class also, but we were only doing the dipole moment, right? So there are three charges, that these are just labels, 1, 2, and 3. And the actual magnitudes of the charges are plus q, and minus 2q. And the position here is, let's say, A. So this could be x equal to 0. So let's say, so this is, let's, as of now, let me just say this is A and this is C. So the charges Q1 is equal to minus 2q. Q2 is equal to plus q. Q3 is equal to plus q. Position R1 is A times I hat plus 0, right? Plus R2 is equal to null. R1 is 0. So the origin. R2 is A times I hat, and R3 is minus A times I hat. And we showed that it's of course charge Q is 0. Like we can do this again. This is of course 0. T, I think it comes out 0, so let's do this. 1 is at 0, so it is minus 2q times 0 as a vector, then plus q times A I hat, and then there is plus q times minus A I hat. So that comes out to be a 0 again. Right? So the dipole moment is also 0. And in these scenarios, it's important, even though I didn't prove it as a theorem, but it can be done very easily. I just illustrated it using an example that if the monopole is 0, dipole is moment at 0, then quadrupole is unique. Then it doesn't depend on its origin, where you put your origin out. So let's do Q now, right? So Q is equal to, so first one is minus 2Q. And remember the definition of quadruple moment. It is 3 times R1, right? So it is 3 times R1, vector R1, minus of 1 times R1 square. So that's what R1 has to do. But R1 is of course 0. So but let's do that slowly. So this is plus Q. That's 3 times R2 minus of dyadic, and this is R2 square. And the third one is plus Q, charge is plus Q, and it is 3 times R3 minus 1. R3 squared. This is of course 0, so this is minus 2q times 0. That whole thing is 0. Forget about that because R1 is 0. Next one, so this is what one should be careful about. These are not dot products, these are not cross products, these are tensor products if you want. These are two quantities that sit next to each other. So R2 is A, so it is 3 times A from here, that's A square, times I hat, times I hat. Right? The new, we write a vector in terms of I hat, but now it is I hat is a component, right? There are 9 components possible. Right? So this is minus of 1. And what is R2 square? R2 square is dot this, right? Dot product of this, that's A square. Do the same thing again here, plus Q. This is squared now, doesn't matter, minus A. So this is again 3A squared. I hat I hat minus 1 dot of this is a square again. That's what it is. We can pull out an a square out of all this, and this is nothing but q times a square. The dimensions of dipole moment are charge times distance square. And what is left is, so this is exactly the same quantity, right? So it is like saying 2 times. So it is 3 I hat minus 1. Remember here, what is I hat is the unit dyadic 1 is I hat plus j hat plus k hat. So if I were to substitute this means that this is qa square times, if I want to write the 2 also inside in the bracket, so there's a 3 I hat, and there is an I hat from here. So 3 minus 1 is 2. So let me put the 2 outside. So this is 2 I hat minus j hat minus k hat. That's what. This can be, if you want to write this in terms of a matrix, this is equal to q a square times 2. These are components of the matrix. This is 1, 1 component. This is 2, 2 components. This is 3, 3 component. And rest of them are zeros. So this is 2 here. This is minus 1. That's a 2, 2 component. Rest everything is 0. That's what it means. Right, this is the I component, this is the IJ component, this is the IK component, this is JI component, JJ component, JK component, KI component, KJ component, KK component. Now only 3 of them survive, so that's your 3 diagonal terms. So that's your quadruple moment. So quadruple moment is a tensor, and that's its shape. For this. And since the dipole and monopole is 0 in this case, this is unique. Wherever you keep your origin, you will always get it in this form. Like any of you guys work it out, it will always come out the same. Where you keep the origin doesn't matter. Any questions? This need not come out so clean. For example, let me begin on another problem. We have about 6 minutes. So this was all on a straight line. I can try to do the quadruple. So another example. Example 2. We can talk about the same distribution. So that's 1, that's 2, and the third one could be here. And let's say this is A, and that's A. So what changes is Q1 is minus 2Q, Q2 is plus Q, Q3 is equal to plus Q. And let's say the position R1 is 0 still. Position R2, it says A times I hat, and position R3 is A times J hat. Most of the things will remain the same here, except so Q here, if you were to do this, the first piece remains the same, so that's 0. Q1 will be 0 still because R1 is still 0. For charge 2, this is still on plus A with respect to this origin. So this will be plus q times 3a square times I hat minus 1 times a square. Now third one will be actually, now is j hat, otherwise it's the same. Minus of 1 is square. And again, one can pull this out, q a square, and put this all together. So this is 3 I hat, and then there is 3 j hat, and minus of 2, 1, right? 2 times 1. Which will give me equal to q times a square. There is a 2 of 1 there, so that cancels one of them. So that's I hat. So 3 minus 2 is just 1 plus j hat the same thing, 3 minus 2 there, and k hat is minus k hat. So if I were to write this as a matrix, this will be q a square is 1, 1 minus 1. In all the examples that I built, it seems like they're all diagonal, but that doesn't have to be the case. We can get non-diagonal terms. Questions? Did I make a mistake? Minus 2 k hat. That's correct. Thank you. It's minus 2 k hat. It's like 3 minus 2, 1. Minus 2, 1. 2 remaining there. Yes. Thank you. Notice that I have taken either along the x-axis or y-axis. For example, if I have a charge somewhere else here, let's say this is A, that's A. So what will that look like? So the quadruple moment due to this point charge, Q, will be equal to Q times the position now, R is AI plus AJ. That's your position. So then you say this is 3 times R again. So this is AI hat plus AI hat. Multiply that again, AI hat plus AI hat minus of 1 times R square, which is, so R square would be equal to A square. A square plus A square, that's 2A square. Right? So that's 2A square. Oh, so this is, sorry, so this is J hat, right? So this is J hat. And now you see the other components coming up. So this is Q A square times 3 times I hat plus I hat J hat plus J hat I hat plus J hat. These are not the same. They're not. Ij is not the same as J. I minus 2 times 1. So this will look like as a matrix, and you can still see yes. So it's Q A square. Write this as a matrix. There's a 3 times I, 2 times I, so that's 1. Right? J hat is 3 minus 2, 1 again. And K is minus 2. But then there are ij terms now. So this is 3 here, and that's 0, 0, 0, 0. This is just 1 point charge sitting in there, and that's a quadruple. That gives you an idea of how to process things. This non-diagonal. I went too fast because I wanted to finish, but I hope that I did that correctly. Yeah. Questions?
That's
Yes.
a separate example.
Yeah, this is a separate. So this was over here. So this is, if you want example 3, yeah, I started hurrying up. So this is example 3, 1 point charge, single point charge. Which is not at the origin, which is placed not along the axis either. So, and once you know how to calculate for 1 pointer, then you can keep adding, right? So that's the main
Because there wasn't meaning, like a quadruple moment doesn't have any meaning for just one charge.
Exactly, it's not unique because it is not 0. Even in this case, actually, this is not unique because this is dipole moment of this is not 0. But you can always calculate it. It's like saying moment of inertia. We do it for different axes. You can use it, of course, but we should be aware that yeah, this is a reference system dependent. But this is turns out to be unique. This one was 0, so that's a good example. In fact, one can ask the question: if you have 3, or there is a theorem like this, that if you have 3 charges, then if the monopole is 0, dipole is 0, 3 arbitrary charges positioned at 3 different points, and if its monopole is 0 and dipole is 0, then they have to be in a straight line. Like you cannot have a quadruple moment for if they are not aligned, then if they are not collinear. Actually, I was thinking of asking an extra credit problem as to find out, can you construct a quadruple moment which is unique, which is not on a straight line? But then I think I went too fast. And there was no extra credit today. Nothing, no extra credit. Okay, thank you so much.